Um, Hi everyone, welcome to my talk today. I'm going to talk about the predictability of genomic changes underlying the recent host shift in Melissa blue butterflies. So there are various contexts in which predictability of evolution has been thought about and conceptualized about. One of the frameworks in which it has been thought about is repeatable and parallel evolution, and one of the classic examples for this is sticklebacks. Another context, a very interesting context in which predictability of evolution has been thought about, is predicting long-term natural variation from short-term experiments. And a recent example for this is parallel divergence in color patterns due to color patterns in stickleback is stick insects. Sorry. What is interesting is that each of these contexts has been thought about individually, but they have been rarely combined, and they've been rarely used together to predict and compare predictability and to quantify predictability. The second interesting thing is that most of the evidence for predictability lies for simple, discrete Mendelian sort of traits, but there's limited evidence for predictability for complex, multifaceted traits such as host plant use. So I'm going to look at both these frameworks together today for a complex trait like host plant use in Lycaeidis melissa butterflies. So, Lycaeidis melissa butterflies have been studied extensively for host plant use. A little bit of background. In the northwestern United States, across their range, they utilize multiple leguminous hosts, which are their native hosts. But recently, since the introduction of alfalfa in the geographic range in the past 500 years, these butterflies are now shifting to this novel host and colonizing this novel host. Along these lines, there's evidence that these butterflies are adapting to alfalfa, even though it's a poor host compared to the native host. So this creates an interesting premise to test for repeatable and parallel evolution in this system, and to ask if we can quantify predictability underlying host plant use in the system. So to do that, I'm going to focus on two main questions today for my talk. The first one being finding evidence for repeated colonization for this novel host in these butterflies. And say we find this evidence, we find there is repeated colonization of this host. I want to ask if we can predict the genetic variation underlying host use in these butterflies. So coming to the first question about repeated colonization, I specifically wanted to ask if Lycaeidis melissa populations have colonized the exotic host plant alfalfa repeatedly. So here we have the map for the populations we have in this analysis. So basically the points indicate all the populations we've sampled so far. The color of the points indicates the host plant these populations are associated with in nature. So basically, either they're associated with any of these three native hosts or the novel host alfalfa. The numbers on these points indicate the 25 populations which we included in our analysis. So we had these 25 populations, we had in total 523 individuals from these populations, and we used a genotyping by sequencing approach, and we identified 206,028 single nucleotide variants for our further analysis. So to test for repeated colonization, we used a population tree approach using tree mix, and we allowed for an admixture model to see if there's any evidence of gene flow between and among populations. So what did we see? So we see that populations first have evolved in these two major clades in this tree. And interestingly, both these clades are interspersed with both host-associated and non-host, native host and novel host-associated populations. So basically indicating that these populations have evolved based on geography and not based on host association. The main point being here that these populations have repeatedly evolved at least in minimum of 2 colonization events to independently colonize this novel host alfalfa. Another interesting thing was the admixture model did not improve the fit of the tree, and we found that there was limited evidence of gene flow between and among populations, indicating that they have independently colonized this novel host. So we found these two major clades, and these are two subgroups of Lysaetes melissa, which concur with the map geographically. So we're going to call them Melissa East and Melissa West, and we're going to use these two subgroups for our further analysis. So now that we've found this evidence for independent colonization events, it makes a good background to test for parallelism in these populations. So we move on to our second question, where we wanted to ask to what extent can we predict evolution of genetic changes underlying host shift. So there were two important points we wanted to test over here, mainly looking at degree of predictability. The first thing being quantifying predictability in the context of these two frameworks, wherein we are testing for parallelism in natural populations, similar to the stickleback example I gave before, and then using data from an experimental setup and asking if we can predict natural variation from short-term experiments in the lab, similar to the stick insect example I gave before. And we also wanted to see we also wanted to compare the degree of predictability between these two frameworks to see if we can predict more, there's higher degree of predictability in one framework compared to the other. And to do this, we used X-fold enrichments, where we mainly wanted to see if the overlap between genetic variants is more than expected by chance. So coming to parallel evolution, we mainly want to see that have independent host switches to alfalfa resulted in parallel evolution at the genetic level. So we again use these two subgroups, which we found in the tree before, the Melissa East and Melissa West subgroups, and we used BayPass, which uses a model which controls for population structure and finds allele frequency and host correlations to find candidate SNPs which underlie host use in these populations. So once we identified those candidates, we focused on the top 0.01% most host use associated candidates. So what we have over here is all the SNPs in the data, and then all the points indicate the SNPs, and then the line indicates just delimiting the candidate SNPs which are most associated with host use. So some of these SNPs showed significant access on Z chromosome and also on the coding region of the genome, which was interesting because that indicates that natural selection was affecting these SNPs. So now that we've identified those top 0.01% candidate SNPs, we tested for parallelism between the two subgroups, and we found that there are 58 SNPs which are parallelly evolving for host use between these two subgroups of Lysaetes melissa. I've highlighted these SNPs in red over here. As you see, these are significantly associated with host use, and again, these are 3 times more than expected by chance, and this is consistent, and there's a modest excess of parallelism. So now that we found this, we wanted to test if this degree of predictability is consistent across different quantiles for different SNPs, and to see if the X-fold enrichment holds for different quantiles of SNPs. So here I have a bar graph, very obvious. But for quantiles of SNPs from 0.01%, which is very limited analysis, to up to 0.1%. And we see that this X-fold enrichment kind of holds across these quantiles. And more interestingly, it gets stronger as we move towards the 0.01%, indicating that the most host use associated SNPs are very significantly enriched for parallel evolution. So now we found evidence for parallel evolution. We found that there is some degree of predictability through this framework. So we moved on to the second framework, and we asked if SNPs associated with host use in nature also associated with performance in the laboratory. So I've been talking about this experiment in laboratory. What is this experiment? So recently we did a study using 2 populations of Lysaetes melissa, a silver lake population which is associated with astragalus, a native host in the wild, and a goose lake population which is associated with alfalfa, the noble host in the wild. And we used caterpillars from both of these populations to do a rearing experiment in the lab to quantify performance on each of the hosts and to find candidate SNPs which affect performance of larvae on each of these hosts. So here I show the SNPs which we found in the study. So basically we have all these points as SNPs which affect performance of larvae on the host. They mostly lie along the axis. There are different SNPs which affect performance of different hosts, and over here we focus on the effect of SNPs on individual hosts, so astragalus and alfalfa. And we focused on the top 1% candidate SNPs found in the study. So now we have these top 1% candidate SNPs from this experiment, and we already found the top 0.01% candidate SNPs in the parallel evolution test, and we wanted to see if there's an overlap between these two. So what we saw is that yes, SNPs associated with survival on host in the lab are also associated with host use in the wild. And again, we see there's like almost double, almost 2 times more than expected by chance, again a modest axis. And interestingly, you see an axis of it in GLA population, which is associated with alfalfa or the novel host in the wild. Again, we wanted to test if this degree of predictability is consistent across different quantiles of top host-associated SNPs. And we again saw that there is a significant enrichment from 0.01% to 0.1% host use associated SNPs, and it's again strong for the 0.01%. So now we found, even in this context, we can quantify predictability, and there is some consistency in degree of predictability. So what are conclusions from this study? So basically, we used both these frameworks to quantify predictability for host plant use. And we could successfully do that for a complex trait like host plant use. Expectedly, the degree of predictability is low. And secondly, the degree of predictability is higher for parallelism, which is, we found almost 3 times more X-fold enrichment for parallelism. And in the comparison from the experiment to natural populations, the X-fold enrichment was just 2. So, which is expected because in an experimental setup, we cannot capture all the variables which are present in the wild. But what is more interesting is the fact that there was not much of a difference between these 2 frameworks. So a similar level of predictability from parallelism in natural populations and from predicting natural variation in the wild from an experimental setup. With that, I will conclude. Thank you.